Hi everybody, welcome back to the channel. In the last video we looked at a couple of different examples of related rates. I wanted to look at 3 examples, but YouTube only allows me to post 15-minute videos, so I had to cut down the time. So I figured I'd make another video with a couple other examples because you can never have too many examples of related rates problems. Okay, so let's go ahead and jump right in. The first example here, which I'm calling example 3 because examples number 1 and 2 were in the last video, says a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. Let's go ahead and pause there for a second. I'm not sure that everybody is fully familiar with what an inverted circular cone looks like. So even though this is kind of step number 2 in our 8 steps, let's go ahead and start by drawing ourselves a picture of an inverted cone. Here's what that looks like. Think ice cream cone. And when it says that there is a base radius of 2 meters, that's talking about this length or this radius right here. And then when it talks about having a height of 4 meters, that's kind of from the center down to the very bottom there. That's what that's talking about. Okay. By the way, these values of a 2 meters and height of 4 meters like this, these are fixed values talking about the lengths in this whole entire cone. So it's not like the cone is going to be getting bigger or smaller as we work through the problem. It stays the same shape. But then, if we keep on reading, it says, if water is being pumped into the tank at a rate of 2 meters cubed per minute. Okay, let's go ahead and pause there a second. Remember, we're supposed to be reading carefully. So when we have 2 meters cubed per minute, we want to think about what does that value represent. And hopefully hopefully a couple of things jump out at you. First of all, the fact that there's a per minute in here means that this should be a derivative. This should be something that's changing, and the meters cubed part should tell you that this is a volume. So this should be something like dV dt. Okay, and so let's keep on going. It says find the rate at which the water level is rising when the water is 3 meters deep. So we want to think about what is it that we're trying to find at the end. It says here, find the rate at which the water level is rising. Okay, so I tell you what, here, let me go ahead and kind of put some more into my picture here. We have water that's being poured into the tank, and right now what we're told is that the water level is increasing, and water is specifically at a height right now of 3 meters. Okay, and the height of the water, I'm going to call that h. That is not a fixed value. As water gets dumped in, h is changing. So what I hope you see from this as we read carefully, it says find the rate at which the water level is rising. What we're trying to find is dh dt. Okay, that's a speed, which is a derivative, so it's dh dt. And then we're specifically looking at the instance where h is 3 meters. Okay, so notice we know dV dt, we're trying to find dH dt, and we know what h is at this particular instance in time. Now here's the issue. We don't really know anything about the radius r of the water level. Okay, we know that the radius of the whole entire big cone is 2, but we don't know the radius of the water level at this particular instance in time. And you might say, well, does that really matter? Is that important? Well, sort of, because if we think about how to relate volume to height, there is a formula for the volume of a circular cone like this. And it may or may not be one that you remember, but it looks like this. Volume equals 1/3 pi r squared h. And here's the problem with this formula. There's a v, there's an r, there's an h. There's actually 3 variables. And the problem is, that's a lot of information we would need to know. We would need to know something about, if we're trying to find dH dt, then we would need to know about V, we would need to know about R, we would need to know about dV dt, which we do, we would need to know about dR dt, which we don't. So there's a lot of information here. And in this problem, this doesn't show up in many problems, but in this problem, we can actually help ourselves out by trying to replace one of the variables with an expression that uses one of the other variables. Essentially we can use substitution. And here's how we're going to do this. Okay, this is going to involve something you've hopefully seen in your past. And I think this might not have been your first thought to think of, but the more examples we do of this, the more practice we get. There might be a couple of other instances where you might see something like this needing to show up. And so if we look at this picture kind of comes from looking at a small portion of the cone that we had. And if we look at this picture right here, here are some things we know. The big triangle that we have, let me use some colors here. The big triangle is kind of this triangle in blue. And then if you notice, we actually kind of have a smaller triangle as well that we could be looking at, which is the triangle in green right there, which is talking about the triangle kind of involving the water level that we have. And so if you remember some things about geometry or maybe from trigonometry, you might have remembered talking about something called similar triangles. And the blue triangle here and the green triangle here are similar triangles. They have the same exact angle measures, and that means the ratios of their sides are equal. So if you know that this side length is 2, this whole big side length in the blue triangle right there is 4. Remember, those were fixed values. We're calling the water level height, even though we know right now it's at 3 meters, we're calling that h, because remember that is changing. And then we could talk about this little letter r right here, which is the radius of the water level, which that's actually changing too. Okay, now if we can replace one of the h or the r and not have the h or the r, not have them both in there, that would be great. So we could just get volume in terms of one of the variables. That's kind of the goal here. Now, since we're finding dh dt at the very end, I think it would be good for us to try to replace the r here with something that has an h in it. We're going to set up an equation using similar triangles. It's going to look like this. You can do this in like 3 or 4 different ways, by the way, so you don't have to kind of set it up as r divided by 2, but that's what I'm going to choose to do here. And this is the little radius divided by the big radius. And so if we're going to do it like that, then the ratios of the sides of the triangles on the other side of the equation, you're going to have little letter h over 4. By the way, you didn't have to use this, just a little refresher on similar triangles. You could have also used little r over little h equals 2 over 4, which is which is the big radius divided by the big height. It actually doesn't really matter. You'd get the same exact thing as an expression for r. So take your pick of kind of how you want to set up the ratios of the sides of a triangle. It doesn't really matter. You'll get to the same spot either way. And what we're going to do here is we're going to solve for little letter r. And by doing that, we're going to get 2h over 4, or another way to write that is h over 2. And so we have r equals h over 2. Now what we're going to do is we're going to substitute in this equation up here. So volume equals 1/3 pi times, let's see, r is h over 2. Don't forget the squared in there, h over 2 squared, times h. And now, if you look carefully at this formula, we have volume written in terms of only one variable, h. There's no more r to worry about. Okay, let's go ahead and kind of clean this up a little bit. You probably know what's coming next. We're going to be taking the derivative of both sides with respect to time and plugging in what we know, if you kind of walk through the steps that we had in our last couple of videos. But let's go ahead and simplify this a little bit first. This is 1/3 pi times h squared over 4 times h. So another way to write this is 4 over 3 pi h cubed. Okay, that's another way to write our volume. Notice we haven't taken a derivative yet, but that's just another way. We can kind of clean it up before we take a derivative. I'm going to go ahead and erase that and give myself a little bit more space here, because again, you probably know what's coming next. We have a formula for volume now, only in terms of one variable. Let's go ahead and take the derivative of both sides with respect to t. So v prime is equal to, let's see, the 3 is going to drop down. Think about a power rule here. So this is actually 4 times pi times h squared. But don't forget, you need a dh dt. And by the way, instead of writing v prime, maybe it would be a little bit more consistent or better for me to make sure that we're being careful that we're taking a derivative with respect to t. So I'm going to, instead of writing it as v prime, I'm going to write it as dv dt. Either way is probably okay, but it's just good to remember that we're taking the derivative with respect to t. Okay? All right, now let's go back and look at what information do we know, and what we want to plug that in and solve for what we're missing. So remember, we know dv dt was given to us. That's 2 meters cubed per minute. So that's 2. Over here we have 4 pi. Let's see, do we know h? I think so. H at this particular moment in time, we were talking about 3 meters cubed, so 3 squared. and then times dH dt. That's really good because remember our goal was to solve for dH dt. So move everything else over to the other side. Let's see, 4 times 9 is 36, so divide by 36 pi. I think you get something like dH dt equals, let's see, 2 over 36, so 1 over 18 pi. And then thinking about our units, dH dt, we are talking about meters per minute, because in our volume we had meters cubed per minute. Okay, so that came from the 2 over 36, and then solving that way. All right, this one's a little bit more complicated because we had to do a substitution in here, but I hope that helps just show another example of a circular cone. Let's take a look at one last example to kind of close up our examples from related rates. This problem says car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So let's start out by drawing ourselves a little picture of the intersection here, and we are told that car A is traveling west towards the intersection. So car A, I'm going to put a little dot over here for car A, and let's see, car B is traveling north at 60 miles per hour. So here's car B. So car A is going that way, car B is going that way, and car A is traveling at a consistent rate of 50 miles per hour, and car B is traveling at 60 miles per hour. Okay. So it says, at what rate are the cars approaching each other? And so really what this is talking about is the distance between them. You can call that C or Z if we're using X and Y, or kind of call it whatever you want. I guess I'll use Z over here. And so we can talk about the distance that A is from the from the intersection. So let's call X the distance from A to the intersection. And then Y we'll call the distance from B, from car B to the intersection. And then Z is the distance between them. And it says, at what rate are the cars approaching each other? What we're trying to find at the end is we're actually trying to find dZ dt. Okay. So we know how far A is from the intersection. We know how far B is from the intersection. We know how fast A is moving. We know how fast B is moving. We're trying to find dZ dt. I think this one's a little bit more straightforward. Should remind you of a little bit of the falling ladder problem that we had in the last video, because we can use the Pythagorean theorem here to relate the two different sides. To do that, that would look like x squared plus y squared equals z squared. And then we need to take the derivative of both sides with respect to t. So we should get something like 2x times dx dt plus 2y times dy dt equals 2z times dz dt. And then we can look back at the previous page and plug in all the information we have. We know that x is 0.3 and dx dt is 50. We know that y is 0.4 and dy dt is 60. And then 2z times dz dt. Now, the problem is we don't know what z is here, but if we look back and use the Pythagorean theorem, we can actually find that z is 0.5. This is like a 3, 4, 5 right triangle. So we have 2 times 0.5 times dz dt. 2 times 0.5 is just 1, so that means that dz dt is equal to the left side, which is 0.6 times 50 plus 0.8 times 60, and whatever you get there is your solution for dz dt. Okay, hope you enjoyed.